Hello, I am Dr. M.G. Vijay from the Department of Physics, Mahatma Gandhi Memorial College, Udupi. I would like to consider the last topic in and Unit 4, that is the cathode ray oscilloscope. From the examination point of view, don't neglect this particular topic. Most probably, you will have one full question on this. So let us see what is cathode ray oscilloscope. It is also known as CRO. It is an electronic device that is capable of producing a visual indication of electrical signal or the waveform. From this particular point, it is different from what is the thing that is present or that you have studied in the earlier part, namely the amplitude modulation or the frequency modulation, in which usually we consider only the audio part, and this is with reference to the visual part. Here it is an instrument which is used to display and measure electrical quantities like the AC or DC voltage, frequency, rise time, fall time, etc. Broadly, we can say a CRO consists of the number of subsystems like cathode ray tube, vertical amplifier, horizontal amplifier, sweep generator, trigger circuit, high and low voltage supply. As I said, from the examination point of view, you are going to get one question, most probably on this particular thing, namely the cathode ray tube or CRT, which is treated as the heart of CRO. This is the block diagram of CRO. It contains these different components. Here, this is what is known as the cathode ray tube. We are going to consider more about this particular thing in detail. Here we have the input signal, which is given to the vertical amplifier. A portion of that is directly fed to CRT, and then another is fed to trigger circuit, to sweep generator, to horizontal amplifier, and then to CRT. And in particular, this particular cathode ray tube operates at slightly higher voltage, and therefore we have high tension supply to this, and all other components are connected to low tension supply. So this is the cross-sectional view of cathode ray tube. It is better if you draw this particular figure and study the different parts in detail with reference to the examination. So this is what is known as the cathode ray tube. Here we have the evacuated glass envelope, EGE. This is made up of glass and it is evacuated. And on one side we have number of terminals here, points. Don't give too much of importance for the number of terminals here. It differs in different textbooks. It is connected to what is known as a filament. So by passing suitable current through this particular filament, it is heated, and then this is covered by a cathode. Thereby, the cathode gets also heated up indirectly, and then that particular cathode is covered by what is known as a grid, which is having finite number of perforations, which means by heating this particular filament, electrons are produced from this particular cathode and they begin to move from the grid. And on the other side, we have what is known as the focusing anode. Now look at this. On one side of this particular anode, there is wide opening, and on the other side, it is small. It works as anode, and also it is used for the process of focusing the beam. And similarly, there is one more anode which is used for two different purposes. Because of this particular channel, you can say it gets focused, and at the same time it is also accelerated, and then the electron beam that comes out through this particular anode, it reaches the point here, and it is possible to apply certain potential by means of these two plates YY dash, by means of which this particular electron beam may be deflected in the upper side or towards the lower side. And then we have two more plates by means of which again the potential may be applied, and by applying suitable potential difference it may be made to move in the x-axis. So this is going to play an important role. This particular plate y dash and this system xx dash is responsible for making either the moment of the beam in the x-axis or in the y-axis. And finally, the electron beam reaches the other end, which is the screen, which is made up of the material glass. And therefore, this particular electron beam reaches the screen, which is coated with the phosphor material. In some of the textbooks, they say zinc oxide or zinc sulfide, both of them are possible. There we have the phenomenon of fluorescence, which means the electron beam reaching on this particular screen excites the atoms or the molecules of zinc oxide or the zinc sulfide, and then while coming back, they produce the bright spot. As a result of it, we are going to see the movement of this particular bright spot when suitable potential difference is applied. At the same time, these charged particles, electrons, are moving and they are hitting these walls of the container. So in order to avoid the presence of excessive charges, there is a coating that is made by means of what is known as the aqua drag. In general, this complete cathode ray tube may be divided into two different parts. This is the electron gun portion or the gun region, and then the deflection region, and then this is the third one, namely this. In general, the signal to be displayed is always applied across the Y plate. To see the waveform, it is spread out in the horizontal direction, which means another voltage is applied to X plates, and in general, that particular waveform is in the form of a sawtooth wave, and therefore it is also called the ramp voltage. Remember, this is the voltage that is applied to the X plates. So when we say the X plate, this is the standard type of the voltage that is being applied, and this is the ramp voltage. and this particular thing gives the period of the sawtooth wave. In order to have a stable stationary display, we have to consider this particular phenomenon, namely synchronization. So, whenever the horizontal sweeping frequency or the period, which may be represented by TSW, is an integral multiple of the input signal frequency or the period Ts, it is said to be synchronized. So the condition is TSW should be equal to n times Ts. So here we can see, so this is the cathode ray tube screen. Let us say this is the screen which is present exactly opposite to you, what you are observing now. And here there is one particular beam that reaches, and then in general, the movement of this particular thing is always in one particular direction, namely y. But at the same time, because of the voltage that is applied along the x-axis, it is moved or it is pushed to the other side. And as a result, when n is equal to 1, that is TSW is equivalent to 1 TS, we have the movement of the beam like this, and it is possible to have one complete wave. And if the condition n is equal to 2 is satisfied, then we are going to get two different beams, two different waves in that screen. And then another important thing with reference to this is what is known as scanning. So the electrical signal is always present in the form of the charge image inside the TV camera. There is an electron beam, and this electron beam moves in a sequential manner. That is, it moves from left to right and then from top to bottom. But this movement that is going to take place is represented, or it is done in two different ways, namely the progressive scanning and the interlaced scanning. So this is the example of progressive scanning. If we say this is the general TV screen, which is true with reference to, or which is independent of the size of the screen, there is always going to be 625 lines, and the first line on the left hand side corresponds to the number 1 on the right hand side, which is slightly below, and then the beam from this particular point begins to move in this particular way. So after reaching this particular point 1, it begins to move towards the left, and then from 2, again it begins to move to 2 and then to 3. Now look at this. This particular movement wherein we have the beam from left to right is what is known as the trace, and the movement from 1 to 2 in the negative direction, or let us say from right to left, is what is called the retrace. And this is how the phenomenon of scanning takes place. And we have what is known as the Consultative Committee of International Radio. And this is the thing that I said. All TV screens are made to have 625 lines. And the complete picture that we get on the screen is called one frame. To avoid flickering, to get the clear picture, one frame is usually divided into two parts. They are called the two fields, and each will be having 312.5 lines. The minimum 25 complete pictures per second is necessary to have a stable picture, but it is desirable to have 50 per second. So the horizontal frequency will be 312.5 into 50, and the time for scanning of each line is the reciprocal of this, that is going to be 64 microsecond. So in the case of interlaced scanning, the scanning of alternating lines and not the successive lines. And here we are going to have the odd line field and even line field. So that's about scanning. And then a small note we can say regarding the monitors. In the case of the cathode ray tube monitors, it is having what is known as a vacuum tube. We have a heating cathode, which is bulky. And nowadays, we make use of the monitors which are LCD, that is the liquid crystal diode monitors, which is actually used in the case of the television screens and the laptops. And here we don't have the vacuum tube or the heating cathode. In the case of LCD monitors, we are now having a very thin one, which may be of the order of half-inch thin thick. It is comparatively low power. It is free from mercury and it weighs less. And this is the LCD technology. The thing is what is known as the cold cathode fluorescent light. We have crossed polarizers between the two. The twisted liquid crystals, they are going to behave in a different way in the presence of the electric field. This cold cathode fluorescent light is usually represented as CCFL. And again, in this, it is the cold cathode, so there is no direct heating of the cathode. It emits electrons and we are going to get the light. And here we have the pictorial representation. We have the crossed polarizers and they are the cold cathode fluorescent light, and this material which is twisted crystals are present in between, and therefore we are going to have the light. And the behavior of the twisted crystals is imparted in the final process of the emission of the light from the electric field. So this is the external field twist. Whenever the twist takes place, the output is going to change. But as an advancement over this, we have what is known as the light emitting diode monitors. This is also used in the manufacturing of televisions and very big screens. So here light emitting diode is used instead of CCFL. So this is the LED screen which is being used, and a tiny little bulb, small one, which is having extremely bright, is utilized, and it uses little power. And from the examination point of view again, this is another small question that may be asked to compare LCD and LED monitors. So here we have the final tabular column. LCD monitor, energy saving, color quality, clarity, refresh rates are comparatively low when compared to the LED monitors. The contrast ratio is low in the case of the LCD monitors, whereas the brightness is going to be the same, and LCD monitors are going to be they weigh more when compared to the LED monitors.